Okay, this is the Professor, CBMD PhD. And today's Friday, May 12th, 2023. It is 4:25 and 17 seconds, AM Eastern Daylight Time. And today's research, optical systems. So let's hop to it here. Leaky wave meta surfaces, a perfect interface between free space and integrated optical systems. Date May 8th, 2023. Source: University of Columbia, School of Engineering and Applied Science. Researchers have developed a new class of integrated photonic devices, leaky wave metasurfaces, that convert light, initially confined in an optical waveguide, to an arbitrary optical pattern in free space. And these are the first to demonstrate simultaneous control of all four optical degrees of freedom, because they are so thin, transparent, and compatible with photonic integrated circuits. They can be used to improve optical displays, LIDAR, optical communications, and quantum optics. We are excited to find an elegant solution for interfacing free space, optics, and integrated photonics. These two platforms have traditionally been studied by investigators from different subfields of optics and have led to commercial products addressing completely different needs. The work points to new ways to create hybrid systems that utilize the best of both worlds: free space optics for shaping the wavefront of light, and integrated photonics for optical data processing to address many emerging applications such as quantum optics, optogenetics, sensor networks, inter-chip communications, and holographic displays. The key challenge of interfacing PICs and free space optics is to transform a simple waveguide, mode confined within a waveguide, a thin ridge defined on a chip, into a broad free space, wave with a complex wavefront, and vice versa. The team tackled this challenge by building on their invention last fall of non-local metasurfaces and extended the device's functionality from controlling free space, light waves, to controlling guided waves. And specifically, they expanded the input waveguide mode by using a waveguide taper into a slab waveguide mode, a sheet of light propagating along the chip. They realized that the slab waveguide mode could be decomposed into two orthogonal standing waves, waves reminiscent of those produced by plucking a string, and therefore they designed a leaky wave metasurface composed of two sets of rectangular apertures that have a sub-wavelength offset from each other to independently control these two standing waves. The result is that each standing wave is converted into a surface emission with independent amplitude and polarization. Together, the two surface emission components merge into a single free space wave with completely controllable amplitude phase and polarization at each point over its wavefront. The team experimentally demonstrated multiple leaky wave metasurfaces that can convert a waveguide mode propagating along a waveguide with a cross-section on the order of one wavelength into free space emission with a designer wavefront over an area about 300 times the wavelength at the telecom wavelength of 1.55 microns. These include a leaky wave meta lens that produces a focal spot in free space. Such a device will be ideal for forming a low-loss, high-capacity free space optical link between PIC chips. It will also be useful for an integrated optogenetic probe that produces focal beams to optical stimulate neurons located far away from the probe. A leaky wave optical lattice generator that can produce hundreds of focal spots forming a Cagon lattice pattern in free space. In general, the leaky wave metasurface can produce complex and periodic and three-dimensional optical lattices to trap cold atoms and molecules. And this capability will enable researchers to study exotic quantum optical phenomena or conduct quantum simulations hitherto not easily attainable with other platforms, and enable them to substantially reduce the complexity, volume, and cost of atomic array-based quantum devices. And for example, the leaky wave metasurface could be directly integrated into the vacuum chamber to simplify the optical system making portable quantum optics applications such as atomic clocks a possibility. A linky wave vortex beam generator that produces a beam with a corkscrew-shaped wavefront. This could lead to a free space optical link between buildings that relies on PICs to process information carried by light, while also using light waves with shaped wavefronts for high-capacity intercommunication. A linky wave hologram that can display four distinct images simultaneously, two at the device plane, at two orthogonal polarization states, and another two at a distance in the free space, also at two orthogonal polarization states. This function can be used to make lighter, more comfortable, augmented reality goggles and more realistic holographic 3D displays. The current demonstration is based on a simple polymer silicon nitride materials platform at near-infrared wavelengths. The team plans next to demonstrate devices based on the more robust silicon nitride platform, which is compatible with foundry fabrication protocols and tolerant to high optical power operation. They also plan to demonstrate designs for high output efficiency and operation at visible wavelengths, which is more suitable for applications such as quantum optics and holographic displays. And this is the professor, professor of space physics, mathematics, computer science, and leader of research. This video was created for educational purposes only. Hope you enjoyed listening. Until next time, have a great day.